also on this, yeah. So this is one of the problems that you sent, what you see over here, a graph of two the independent variable v and the dependent variable, I think this axis is going to be u, this is just u, right? The graph of this figure specifies a functional relationship between two variables u and v. As I said, this axis, the vertical axis is u and the horizontal axis is v. The question is, part A, find this integral u dv from v is equal to a to v is equal to b. Sorry, not v is equal to a. From the point A to point B, okay? Well, it's an integral, right? But it's very clear, if you see the graph, is that the relation between u and v is linear, right? This is obvious. U and v, u and v are linearly, we say linearly dependent variables. Well, if you see u as the dependent variable and v as the independent variable, then you can say u is a function of v, okay? U is a function of v, but what kind of functional dependence is that u increases linearly as v increases on this axis. So this is what a linear dependence means, okay? And whenever you see a straight line, it's obvious that it's straight line. Then there is the relation between these two variables are linear, okay? And the next thing you have to do is you have to specify these points A and B. What are these points in terms of u and v? All right. But it's very clear from the picture that by looking at this scale, okay, if you look at the scale in the u and the scale on the v, you can just find these squares in units. Well, if the two squares in the vertical direction is 4 units, and that means one square is going to be only 2 units, okay? Similarly, if two squares in the horizontal direction is 10 units in units of v, one square is going to be just 5, right? So specifying the point A means that what is v at point A and what is u at point A. So first, let me put over here, let me put over here, A, the point A is nothing but the first is two numbers. You have to give two numbers over here, but the first number is going to be the value of v at point A. The value of v at point A is nothing but it is 5, right? Because 2 squared is 10 and 1 squared is going to be 5. So you just put 5 over here. And the value of u at the point A, it is the second number in this over here, is going to be the value of u at the point A. It is minus 2, right? Because 1 square is 2 units, but it's just below the origin, so it's going to be minus 2. So over here you've just put minus 2. This specifies the point A. And as I said, this first number represents the value of v, and the second number represents the value of u. And if you do this same thing with b, you just find what the value of v at the location of point B. It is just between 20 and 30, so it's going to be 25. The first number is 25. And for the value of b on the u axis, it is just 8. So it is 8 over here. I hope this is clear. So the first thing first is to do is just specify the points A and B in terms of u, the v, and u. All right. So now next comes to the question part A. Find this integral. Find the integral from the point A to the point B, integral of u dv. Okay. So what is u dv? And I'm sure that you have seen this in calculus, that when we are taking integral, we represent the integral sometimes as the area under the graph, right? Because what you see over here, the integral of u over the variable of v. So u is in that case a dependent variable and v is independent variable. But u is a function of v, and integral of u as a function of v is nothing but, we have seen, the area between this line, the line, and the horizontal axis. Okay. If if you look at this, this is going to be the area of a triangle, because the graph is just a straight line, and the projection of this straight line onto the horizontal axis is going to be this area. Okay, let me just shade it. Okay, I'm trying to shade it. So this is the triangle. Okay, this is the triangle that you want to calculate if you want to find this integral. And this integral corresponds to nothing but the area of this triangle. Okay, this right triangle. But you have to be careful in finding this area, because finding this area means that you're going to, if somehow the triangle, some part of the triangle is located under the horizontal axis, then in that case this part of the area is going to be taken as negative. Okay, and the part of the area that is above the horizontal axis is going to be taken as positive. All right, so I hope this is clear. Now first you realize that this integral is nothing but the area under the curve, which is a straight line in our case, and that means you have to calculate the area of this right triangle. Okay, but when calculating the area, you should be careful that if the area stays, part of the area stays just below the horizontal axis, that part is going to be taken as negative. This part is negative, and this part, the part which is above the horizontal axis, is going to be taken as positive. So you just count the number of squares, right? And if we are taking, if we want to calculate the positive area, that part, it is nothing but half of all the squares, the number of squares, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 squares, but half of it is just 6 squares. So the positive part of the area is just 6 squares. Let me put this 6 squares. This is the positive part, and the negative part is 1, 2, 3 and a half. Negative part is minus 3/2 squares, right? So if you add this, positive 6 squares, negative 3.5 squares makes positive 2.5 squares. right? So this is going to be just the result of this integration, u dv, from the point A to point P, okay? So 2.5 squares, but what is the area of one square? The area of one square, since this side is 2 and this side is 5 in V, it is 5 in U, this side is 2. 2 times 5 is nothing but 10. You multiply this 2.5 squares by 10, it is going to be 25 square unit. Square unit. So the result of this integration is nothing but 25. Okay. So this is one way to calculate this integral, just realizing that this integral is nothing but the area under the curve, as you did in calculus course. Let me put over here the unit, okay, unit square. Anyway, whatever the unit for u multiplied whatever the unit for v, this will come over here, okay? All right, so that's it for the part A. If you have any questions for part A, just you can ask, okay? Of course, this is not the only way to calculate the area. All right. Sorry, this is not the only way to calculate this integral. You can always do this. You just express this functional dependence between u and v, because u is a function of v. What is going to be the functional dependence between u and v? It is going to be an equation of line, right? Some slope multiplied by v plus, let's say, some constant c. This is the functional relation. Why? Because when you look at the graph is a straight line. If u and v are related to each other by a straight line, then this is the most general expression if you want to express u in terms of v, okay? So u is a function of v. So u is some constant m multiplied by v plus some other constant. So the next thing is to find these constants, and m is nothing but it is the slope of this line, right? And you know, the slope of this line can be easily calculated. Since it is slanted to right, the slope is going to be first positive, and the slope is going to be just, if you look at this right triangle, it is going to be just this side, the vertical side, divided by the horizontal side. And the vertical side is 1, 2, 3, 4, 5 unit in terms of u. But 1 unit for 1 square for u is just 2. So 5 means 10 units of u, okay? So m, I'm just trying to calculate the slope m. If you go 2 by 2, it is 2, 4, 6, 8, 10. It is 10 divided by, if you want to measure the horizontal distance for this side, and each square is 5 unit for v, it is 5, 10, 15, 20, right? So it is 20. The slope is 0.5. So this functional relationship, the first parameter is just 0.5 times v plus, so how do you determine c? When v is equal to 0, c becomes the value of u, right? And where is v is 0? Okay, when you look at the graph, well, when u is 0, we see, no, yes, no, yeah. When you can put this, when v is equal to 25, u is just 8. So put u is equal to 8. This is 0.5 multiplied v. When u is equal to 8, v is nothing but 25 plus c. So from this equation you can find what the c is, and c is going to be 8 divided by half of 25 is nothing but 12.5, right? So c is nothing but, sorry, it's not that, 8 minus 12.5. Sorry about this. So 8 minus 12.5 is nothing but minus 4.5, I guess. So c is minus 4.5. So you can put just minus 4.5. All right. So what's next? You just found the complete relation between u and v as this equation. U is equal to 0.5 multiplied by v minus 4.5. Okay? So you can put this function onto this integral. And since the integration variable is v, these a and b values are going to be v of point A and v of point B. Okay, let me put over here. Since the integration variable is v, well, this question turns out to be a calculus question, right? But why we are doing this? Well, it is one of the questions in the chapter 6, I guess, or 7. This is important because, you know, the calculus problems sometimes turn out to be physics problems. Well, this calculus problem turns out to be calculating the area of some region in a coordinate system. Okay, and probably we are going to use this, apply this methods on calculating the work done by a variable force. This is why we are working on this problem. Okay, you might ask yourself, okay, but this is nothing to do with the physics, but you know, this is the technique sometimes that we are going to use in physics to calculate some physical quantities. That's, you should bear in mind in that way. Okay, so I was talking about putting these a and b values. Since the integration is on the variables of v, then instead of a, you should put what is the v value of a, point of a, what is the v value. So lower value on this integral is going to be 5, because the point A has the v value of 5. Why? We put the 5 over here because the integration variable is v. Okay? And what about the point B? You will just put on top the v value of point B. But the v value of point B is nothing but 25. Okay? And now, what is u as a function of v? U, just put this expression, 0.5 times v minus 4.5 times dv, and calculate this integration. Well, this integration is very easy, should be very easy for you, because what is the integration of v dv? V dv is v squared over 2, right? And since you have a multiplication constant 0.5, or put the 1 over 2 over here, 1 over 2 v squared divided by 2. And what is minus 4.5 dv? It is minus 4.5 v. Minus 4.5 v, the integration of the second term. And this is the result, but this result is going to be evaluated between points 5 and 25. V is equal to 5 to 25. So the result is 1 over 4 v squared is 25 squared, okay, minus 4.5 multiplied by 25 minus 1 over 4 5 squared minus 4.5 multiplied by 5. So you just plug and chuck this expression in your calculator, find the result. But the result is going to be just 25. You can check it. Okay, it is going to be 25. So I just solved the integral of this, integration of this, in two ways. One is by using the graphical method, just calculating the area under the curve, and the other is by using the functional, finding the functional relationship between u and v and calculating the integral straightforward. So there are two ways, but you see the first method is much easier than this one. If you just realize that integration is nothing but the area under the curve, and our curve is here is very simple curve because it's straight line. So area it is very easy to calculate the area of a triangle, and what you do is just calculate the area of this triangle, keeping in mind that if a portion of the area is under the horizontal axis, is going to be taken as minus. Okay. All right. So that's it. I mean, this is the first part. If you have any questions, you can ask. And I just solved the first part in applying two different methods. Okay. So, what's next? Next is the other question is part B. Find again the same u dv integration, but this time the problem is just change the limits of integration. The first one was from a to b. The second one is from b to a. But you know, we know this in calculus. If you want to just interchange the limits of integration, whatever it is, from let's say a to b, is going to be nothing but minus of b to a. So what if you know what the integration of from a to b, then the integration of the same thing from b to a is going to be just negative of the value of over here. So it's going to be just minus 25. The second part is minus 25 because the first part, the answer to the first part is 25. The answer for the second part is minus 25 because of the reasons that I explained over here, switching the order of the integration in the integral. Just it is switches from plus to minus, or from minus to plus. It switches the sign. All right. So what's next? Next is the part C. This part, but for this, let me erase this part. Okay. I have to erase because I have no enough space. All right. So let me erase this whole thing also. So what is the integral, part C? The integral from a to b v du, v du. Well, the integration for parts A and B was about integration of, for part A, integration of u dv. It was u dv, but this time the problem is asking to calculate v du. Well, what's the difference between these is that in this part C, the independent variable now is u, which was the other way around. In the part A, the independent variable was v, but this time the independent variable is u. Okay, and calculate v du. Remember the functional relationship between u and v was u was equal to 0.5 times v minus 4.5. So to calculate this integral now, you have to first express v as a function of u. This is expressing u as a function of v, but now we express v as a function of u. How do you do it? Well, it's easy if you look at it. If u is just this 0.5 times v minus 45, just solve this equation for v. If you solve this equation for v, you can do this. You can put the minus 4.5 on the other way, on the left hand side. Is going to be u minus 4.5 is equal to 0.5 times v. And if you divide both sides by 0.5, v is going to be 2 times u, right? Minus 2 times 4.5, right? Because if divide this by 0.5, it is multiplying 4.5 by 2, it is going to be 9. So this is the functional relationship between v and u as v dependent variable and u independent variable. But for part A, the functional relationship, the same functional relationship, it was expressed as u as dependent variable, v as independent variable. Over here, u is independent variable, v is dependent variable. Okay? So, I mean, the rest is easy because all you have to do is you just put v as the function of u and calculate the integral. So, but for point A and B, for points A and B, you have to put for A, point A, the value of u, and for point B, you have to put for point B the value of u again. For point A, the value of u is minus 2, and for point B, the value of u is 8. You see, now the limits of the integration is changed, different than in the case of part A. Part A was from 5 to 25. Now part C is from integration is from minus 2 to 8, because the independent variable is changed. Okay, although the points are the same, the limits are going to be different, because in compared to the part A, in part A it was from 5 to 25. Now it is from minus to 8, because the independent variable is changed. The independent variable for part A was v from 5 to 25. Now for part C, the independent variable is u, and the limit is just, you're going to use the second numbers in these parentheses, minus 2 to 8. Okay, and put this functional relation 2u minus 9 du, and the integration. Yes.
O 2u artı 9 olması gerekmiyor muydu?
Yes. Thank you for correction. All right. Just my mistake when expressing v in terms of u. This minus is going to be plus if you put on the left hand side. Yes. So next is, it's straightforward integral. The integration of u, the u is u squared over 2, but we have in front of it, that's the factor of 2, is going to be u squared plus 9u, and these are going to be evaluated from minus 2 to 8. So the result is 8 squared plus 9 times 8 minus 2 squared plus 9 times minus 2. If you calculate this, that's the result. It's going to be different in compared to part, I think, A, I guess. Might be the same, I don't know. But the slopes are different anyway. It is different. The slope is in that case it's 2, but the slope was only 1/2 in the first part. All right, so that's it. But again, there is a second way of calculating this integral for part C, as I did in the first part. Instead of calculating this integral, you can just calculate the area between this line and the vertical axis. Okay. In the first part, you just calculated the area between this line and the horizontal axis because the horizontal axis was an independent variable. But this time, you just find the area between this line and the vertical axis. What I mean is that you just find the area of this trapezoid, yamuk. This is a trapezoid. Okay. This is a trapezoid, yamuk, and you will find the area of this region, this region. Well, it's again easy. You can just count the number of squares. Well, this time there is no any part of this area that falls to the left of this line, so that means you count all squares as plus. So 1, 2, 3, 4, 5 squares plus the number of squares, half of the number of squares on this rectangular region. On this rectangular region, 1, 2, 3, 4, 5, 1, 2, 3, 4. There are 4 times 5, 20 squares, but half of it, 10 squares. 10 squares over here. 1, 2, 3, 4, 5. 5 more means 15 squares. 15 squares, but each square was I think 10, because one side is 2 and the other side, one side was 5, the other side is 2, so the unit for the square for one square is 10. Multiply this by 10 is going to be 150. So the result is going to be 150 if you calculate this whole thing. You see, again, it's much easier to calculate. This is 150. It's much easier to calculate this integral when you look at the problem as calculating the area between this line and the vertical axis. It is much easier, you see. This is the second way. Okay, so this is the solution of this problem, and it took long, but anyway, you have just learned some physical representations of what it means to calculate some integrals in physics. As long as you see a graphical representations of these quantities, dependent and independent variables, instead of finding the functional relationships between them and taking the integrals, instead of this, you can just count the number of squares, because you are given also the picture over here. You can just count the number of squares to find the result of the integration. Okay. Any questions on this problem? So this problem, I think it's chapter 7, the problem number 30. The next problem is this one. Let me erase all this. So the question is about, I think, calculating the work done by a force, but force is not a constant force. It is a variable force, and it is given in as a vector. All right. So its x component is 4x and its y component is 3y, and it says that x and y's are in meters and the force is in Newton. It is acting on an object, and this force moves the object in the x direction from the origin to x is equal to 5 meters. Well, the value of x at origin is 0, so that means calculate this integral from x is equal to 0 to x is equal to 5. But first you have to express the integrand, right? How do you express this integrand? This does not belong to the question. So, what is this? Well, we know what f is. F is given as 4xi plus 3yj, right? What about dr? There is a second vector over here. And this second vector is just multiplied by force f. So what is dr? dr is dx I plus dy j. You should know this, okay? Because r represents the position. If r represents the position, r is nothing but, the vector r is nothing but xi plus yj. And if you take differential of this dr, since the only variables are x and y, because I and j's are constants, it is going to be just dxi dyj. So that's it. You should know this, okay? It's easy to multiply these two vectors because it is going to be multiplied by the x components plus the y components. So f dot dr is nothing but multiply the x components, 4x dx plus 3y dy. That's it, okay? So this is the integrand. The work is equal to the integration of 4x dx plus 3y dy. Well, when you look at this integration, you see that integration variable for the first term is x, but the integration variable for the second term is y. Okay? Well, these are two separate integrals. 4x dx plus integral of 3y dy. Well, do you know the integration limits for this first part? Since our integration variable is in x, when you look at the problem, that the object moves from 0, x is equal to 0, to x is equal to 5. So the first integration variables are from 0 to 5. What about this one? It says the object is going along the x-axis. You know, when you just draw the picture for the object is on the x-axis, and it moves on the x-axis from 0 to 5. So on the x-axis, what is the value of y? On the x-axis, the value of y is 0. If the value of y is 0, the force component, the y component of the force is just 0. So this part has nothing to do with the integration. This part is 0. I hope this is clear. And the next is just calculate this integral. It's very easy, piece of cake. 4x integration is 4x squared divided by 2 from 0 to 5. And this is 2x squared from 0 to 5. It is nothing but 2 multiplied by 5 squared. It is 50 joules. So the work done by this force is 50 joules. Okay? Any questions? No questions? Okay. So let me erase this again. Next question. Okay, next question is I think again it's chapter 7, problem number 16. Well, the text of the question is long. I should read it. In a control system, an accelerometer consists of a 4.7 gram object sliding on a calibrated horizontal rail. A low mass spring attaches the object to a flange at one end of the rail, and grease on the rail makes static friction negligible but rapidly damps out the vibrations of the sliding object. When subject to a steady acceleration of 0.8 grams, the object should be at location 0.5 centimeters away from its equilibrium position. Find the force constant of the spring, K. For that question, well, you know, it is a spring mass system, and usually what accelerometer is a device that measures the acceleration of an object or a system, and there is one in your pockets. Your all cell phones consist of this kind of accelerometer. Well, there are no springs on your cell phones, but instead of springs, they use a different system, just acts like a spring on a test object. So by this way, if you know the spring constant, you can just calculate the acceleration anyway. But if you want to calculate acceleration, you have to know what the spring constant is. This question is about calculating the spring constant, and it says that when the acceleration of this 4.7 gram object, all right, if you convert it to a kilogram, it's going to be 4.7 times 10 to the minus 3 anyway. And there is always this relation. We know that since wherever you are at on the spring mass system, measured from the equilibrium, where the equilibrium represents that the spring is neither stretched nor expanded, it has only zero force on the other hand. So this is the equilibrium. But you just replace the object from the equilibrium a distance of given over here, a distance of 0.5 centimeters, and the object acceleration is given as 0.8 g. Well, g represents 9.8 meter per second square, because g is the gravitational acceleration. The acceleration of the object is given, the mass of the object is given, the equilibrium position, the position of the object from the equilibrium is given. So all you have to do is, in this equation, k times x is equal to m times mass, calculate k, solve this for k. Because you know that every spring, if it's displaced from the equilibrium not much, obeys this law that x, the distance displaced from the equilibrium, multiplied by the spring constant, will be equal to just mass of the object that is attached to the end of the spring multiplied by acceleration. We know this equation, all right? And when you know this equation, if three of these quantities are given, you can find the fourth one, which is what we are doing over here. The k is asked in the question, so just solve this equation for k and put all the values given in the problem. That's it. Okay. All right. But the wording of the problem is long, so probably you might not understand the English of the problem. To just change whatever it said over here to this picture. This is the relevant picture. It's about a spring mass system. Whenever is talking about spring mass system, just draw this one spring, and on one end is some mass attached, and the other end is just fixed, and do the rest. All right. Any questions about this problem? So if not, then switch on the next question. So that question is again, I think, from chapter 7, work and kinetic energy. What you see over here is the problem gives a variable force which is acting on a particle, on an object, and it asks about the work done by this force on this object, because we know its functional dependence, the position dependence of the force. Giving this graph lets you know that what is the force at any location. For example, at 4, x is equal to 4 meters, the force is on the object is nothing but 6 newtons. For example, at let's say somewhere over here at x is equal to 6 meters, the force on the object is just 3 newtons, right? So the force at any location when displacing this object. If you know this, you can easily calculate this integral always, because the work is always given by this expression fx dx, right? But as I just solved in the first problem, calculating this integral, if you are provided by the graph of the force, is nothing but calculating the area under the curve. That's what just I did in the first problem today I solved you. The first problem today I solved you was a long problem and calculating these u dv duv integrals. But what I did over there is I showed you a simple way of calculating these integrals by just converting this problem to calculating the integral under a curve. But again, in this problem, this curve is just straight lines, and calculating the area under these straight lines are much easier, right? And the other thing is that this is the only way that you should do over here, because there is no any functional dependence of this fx to x is given to you. Either you just sit down and calculate the functional dependence. It's going to be a long way. Well, you can do it, and I suggest you to do it, because it's just an exercise for you. But instead of that, you just calculate the area under the curve. So the first part of the problem is calculate the work done on this particle from x is equal to 0 to x is equal to 8 meters. So from x is equal to 0 to x is equal to 8 meters is nothing but this area, whole of this area, right? This area, all of this area, this triangular region. So how do you calculate this triangular region area of this? Just count the number of squares, and you can just calculate the area of one square over here. The area of one square is this is 1 unit. One square is 1 unit in the direction of x, and one square again is 1 unit in the direction of force. So one square has the unit of 1 Newton meter. One square is 1 Newton meter, because the unit for the x direction is meter, the unit for the horizontal, the vertical direction is Newton. So the area unit is going to be just Newton meters, Newton multiplied by meters. But Newton meters is just joules, right? So area of one square is just 1 joule, and that's easy because just count the number of squares. If you want to count the number of squares, is you can divide this triangular region into two half rectangular regions. The first one is this one, and the second one is this rectangular region. And calculate these rectangular regions and just divide by 2. So this region is 1, 2, 3, 4 squares. 1, 2, 3, 4, 5, 6 squares. 4 times 6 is 24. Half of it is 12. This part is 12. Again, it's 6 multiplied by 1, 2, 3, 4. Again, it's the same, right? This side is also 12. So total is the work done by this force from 0 to 8, fx dx, is nothing but 24 joules. Okay? You got this? Alright, so next is calculate the work from x is equal to 8 meters to x is equal to 10 meters. So it is asking the area of this triangular region, this region, okay, the area of this triangle from x is equal to 8 to x is equal to 10. This is 10, but remember that from x is equal to 8 to x is equal to 10, the force is negative, while the particle is going in the positive direction, the force is negative, so the area is going to be negative, obviously, and the work done is going to be negative. So the work done is going to be just, again, the number of squares or under this, the number of squares of this triangular region is 1, 2, 3, 1, 2, 6 divided by 2, it is 3. So it is 3 squares, and 3 squares is nothing but work done from 8 to 10 fx dx is minus 3 joules, because it is 1, 2, 1, 2, 3, 6 squares, but half of it 3, and since it's under the curve, it is minus 3. And next is from x is equal to 0 to x is equal to 10. Well, it's easy because it is just sum of these two works. Let's this is put this under w 0 to 8, from 8 to 10. So the work from 0 to 10, it is going to be work from 0 to 8 plus work from 8 to 10, right? It is going to be sum of these two. It is going to be 21 joules. Positive. Okay. It is that easy. I hope it's clear. Is it? Is that clear for you?
Sir,
Yes.
I think there's a problem
Is it?
on B option.
The part B? The part B from x to 8 to x to 10. Yeah. From here to here. What is the problem?
It should be 4 multiplied by minus 3 over 2.
Well, let's do it again. Area of one square is just 1, right? You agree with this?
Yes.
Okay. So from 8 to 10, the area is just the area of this small triangle, right?
Yes.
And just number of squares is 1, 2, 3, 4, 5, 6. Half of it 3, right?
Yes.
So it's
Yes.
minus 3.
Okay, sir.
All right.
Okay, sir.
All right. So any other question? If not, I may continue for the next problem. This is recorded anyway. I will put all these solutions on YouTube channel or also on UBS. All right, so next question. This is the next question. Is it coming from you? This question is not coming from you. I think, selecting this problem on behalf of you, but there are problems that did anyone ask this problem? Did anyone of you ask this problem on Canvas? If not, I will just skip this and I will solve this later, but I will just solve the ones that comes from you, the questions. I think this was not the problem that is sent by you. Also this one, also this one. But this one, yes, this one is sent from one of you. One of your friends that sent this problem. I think this is one of the quiz questions in Canvas. Alright. So, what is the problem? Okay. There is this spring. The spring is, in the vertical direction. But, the spring is just fixed on the bottom. And the top point is just free to move. It is put on a tube like this. And what you see on the picture part A, the spring you see on a relaxed state. On the relaxed state of the spring, the length of the spring is just 16 centimeters. And suppose that the spring mass is negligible, okay? Because, usually if you do this, put the spring on the vertical direction, because of the gravity, the spring will a little be stretched, right? But because of its weight. But suppose that also it says over here, ignore the mass of the spring, that you can take the 16 centimeters as the relaxed length of the spring. Later, some load, some object is just put on this tube on the free end of the spring, and of course the spring will be stretched downward until to a point that the spring distance from this end is just from the bottom is measured to be 6.4 centimeters. Well, at the same time, in addition to the weight of the load, weight of the mass, there is this extra force P is also applied in the downward direction. Okay. So the problem is that to find this force P, if you know the mass of this object, which is given as 0.36 kilograms, can you find what this force is? By just using this information that the spring is compressed to a position measured from the bottom, it is 6.4 centimeters. Or this is the question. Well, let's think over it. First thing is that on this picture over here, from the equilibrium, which is this part, which is this level, from the equilibrium, we just compress the spring to this position. All right. Let me draw also the level of this end, and this is the level of this end. So first you have to realize that this distance is just the compressed distance of the spring, right? If you measure from here to here, this is the compression, and the compression is, you can calculate, it is 16 centimeters minus 6.4 centimeters, right? So this is 16 minus 6.4. Do you agree with this? And it is going to be just, I think, 9.6 centimeters. So the compression of the spring is just, first you have to determine 9.6 because of the reasons that you obviously see in the picture. And this is the compressed spring that, when you put this, express this force on the spring, spring force, which is K times X, right? Wherever you see this X, this is the X value, compressed value for that force. I mean, this is the force, which is F is equal to K times X, and X is 9.6. This is the force applied by this free end of the spring onto object, onto this load. This is the force, okay? But since the system is in equilibrium, when you push the force, P, extra force, together with the weight of the mass, the spring compression is at this level. So you can hold it over here. It is going to be in equilibrium because it's not moving, neither up or down. by the help of this extra force P together with the weight of the mass. This is the position you can take as the equilibrium between the weight of the object plus P and the spring force Kx. So at this point, I'm just drawing over here. There are two forces. One is P plus mg downward, and the other is the spring force, which is K times x upward, right? Because if you compress spring, the spring will apply a force in the direction of opposite to the compression. You compress downward, the spring will apply a force which is upward. It is going to be K times x over at this point. But at this point, the compression is because of this P force together with the weight of the spring, P plus mg. So these two forces must be equal to each other, because they just, cancel each other so that you can hold the spring at this level. So that means Kx is going to be equal to P plus mg. This is the equation that you have to solve, because the problem is asking what the P is. P is going to be just Kx minus mg. And Kx, K is given as 800 multiplied by x is 9.6 centimeters, but you have to convert this to meters, minus mg, m is 0.36 kilogram, multiplied by g is 9.8. And if you solve this, this is going to be about 73 newtons, I guess. Just check it, okay? Alright. Merve sormuştu galiba zaten bunu. Right.
Evet hocam.
Okay. So, any questions on this? If not, I will erase this part. Okay. What next? Next is, again, I think this question comes from you. One of you has asked this question. And again, it's chapter, I think, 7, the problem number 50. Or maybe chapter 8, I think. Or 7, I don't know. Anyway, whatever it is. A single conservative force acting on a particle within a system, whereas the force expression is given minus a times x plus b times x squared I. I means that it is in the direction of positive extraction, but the component is minus a times x plus b times x squared. A and b's are constants, and x is variable, of course. Calculate the potential energy function associated with this force for the system, taking u is equal to 0 at x is equal to 0. Alright, first in first part, what is ux? Potential. And if you have already watched my video about the energy, work and energy, kinetic energy theorem, also conservation of energy, in there are these special forces that are called the conservative forces. If you have a conservative force acting on your system, you can find the potential energy associated with that force, and this is given by this expression. The force, if the force is in the x direction, Fx is going to be nothing but minus of du dx. The derivative of the potential function with respect to x and take the minus of it will give you the force component. And by using this, the problem is asking find this u, okay? Well, if you want to solve this equation for u, I think you have to do some integration, right? Because if you have this expression, that means du is nothing but minus fx dx. Okay, you can work on this equation. It's a differential equation, in fact, and the differential of both potential is going to be the force component minus of the force component multiplied by dx. And from this, if you want to find u, you have to take the integral of both sides, right? And since u is given at x is equal to 0, the right hand side of this equation is integration over the variable of x, and you can put the lower limit of the x to be 0. When x is equal to 0, the left hand side of the limits of the integration is going to be u when x is equal to 0, u when x is equal to x. Okay, so when x is equal to 0, the problem gives you that u is equal to 0, so again you have to put 0 over here. When x is equal to x, u is going to be ux, or function of x. So solve this integration, and this is going to be ux, right? The integration of du is just u, and the lower limit is 0, upper limit is ux. Ux minus 0 is ux. So the right hand side is put fx. What is fx? Fx is minus a times x plus bx squared. So 0 to x minus, we have minus in front of it, minus a times x plus bx squared dx. Okay, all you have to do is solve this integration. All right, so solving this integration is ax together with two minus signs of plus ax, a times x squared divided by 2 minus bx squared minus 1 over 3 b x cubed. And from 0 to x, it is just ax squared divided by 2 minus bx cubed divided by 3. That's it. This is the result. The potential energy is given by this expression. So this was the question. Calculate the potential energy as a function of x. It is this. Okay. Next is find the change in the potential energy and the change in the kinetic energy of the system as the particle moves from x is equal to 2 meters to x is equal to 3 meters. Okay. Well, if you know the potential energy as a function of x, then the change in the potential energy while the particle goes from x is equal to 2 to x is equal to 3 is nothing but is u x is equal to 3 minus u x is equal to 2. This is the change in the potential energy while the particle is going from 2 to 3. Okay. Okay. So all you have to do is just on this expression put x is equal to 3 and take the difference and put x is equal to 2 and calculate the difference. That's it. Man, you can do it yourself. I'm not going to do it over here. It's easy. Well, this result is going to be not a number, but something in terms of these constants a and b. When you put the x is equal to 3 and x is equal to 2, take the difference, you will find something that is in terms of a and b. Okay. Well, this change, one thing is that this change in the potential energy going from 2 to 3, x is equal to 2 to 3, is just going to be negative of the work done by this force from going from x is equal to 2 to 3. Okay? So whatever you find in this part B, it is going to be just negative of the part C. So the change in the potential energy is nothing but the negative of the work done by this force, Fx. Whatever you find delta U in terms of A and B, part C answer to part C is going to be just negative of this answer. Later I will do one more example for this kind of problems, giving numerical examples. Okay, I will do it, but this problem is just asking the results in terms of these constants A and B. Okay, is that understood? And of course, the change in the kinetic energy is going to be this. We know that between the work and the kinetic energy, change in the kinetic energy, we have this relation. By finding this, the change in the kinetic energy is going to be just negative of this change in the potential energy. Okay. So if you have no question on this, we can move on. I will do one more example on this question, this type of question, change in the potential energy, express this change in the potential energy to the work done on the system, also to the kinetic energy change. We will do all these kind of problems more and more. Okay, so this was one of them. All right. So if you have no question on this problem, then let me erase. And switch to next problem. Okay, so this is the next problem. And the problem is when a 4 kilograms object is hung vertically on certain light spring that obeys Hooke's law, the spring stretches 2.5 centimeters. If the 4 kilogram object is removed, how far will the spring stretch if instead of 4 kilogram object 1.5 kilogram block is hung on it? Let's think on the first part of the problem first. So the problem says that you have a spring and in its relaxed position it has some distance from the ceiling, but when you hang an 4 kilogram object, is that 4 kilogram object attached to this end, when you leave it, the object stretches 2.5 centimeters with respect to its original relaxed position. So this distance is going to be just 2.5 centimeters when a 4 kilogram object is attached to the end of the spring. But it says when you remove this 4 kilogram object, if you put only a 5.5 kilogram object, attach 1.5 kilogram object to the end, the question is, what is going to be this stretching distance for 1.5 kilogram object? If you know that for 4 kilogram object it is 2.5 centimeters, what is going to be for 1.5 kilogram object? Well, obviously you have to find the spring constant, I think, right? Because when you attach the free end of a spring and a mass, a load like this, and the system now comes to a new equilibrium position, because at this new equilibrium position, again, the system is not moving, This is the first equilibrium position when there is no mass. This is the second equilibrium position when there is this attached mass. Well, can you say that there is no any force acting on this load? Of course not, because there are two forces acting on this 4 kilogram watch. One is its weight, which is mg downward, and the other is the spring force, which is upward, right, kx. So you have to equate these two forces because they are opposite to each other, and the other thing is that the system is in equilibrium. If the system is in equilibrium, all forces must be add up to 0, but the forces are in the upward direction kx, in the downward direction mg. So if this is it, kx must be equal to mg. And we know x, it is 2.5 centimeters. We know m, it is 4 kilograms. We know g is 9.8. So you can find what the k is. First, mg divided by x. 4 multiplied by 9.8 divided by 2.5 times 10 to minus 2, because we have to convert centimeters into meters. And in the second case, again we have these two forces acting on the 1.5 kilogram object, kx upward, and for this time x prime, let's say, because this x and this x are different, and this one m prime times g, because this mass is not equal to this mass. So in the second case, again you just put kx prime is equal to m prime g, but this time you don't know what x prime. If you leave x prime alone, m prime g divided by k, and m prime is this time is 1.5 centimeters, sorry, 1.5 kilograms. G is 9.8. Multiply this by 1 over k, and k is this one, 2.5 times 10 to minus 2 divided by 4 times 9.8. So you can cancel these 9.8s, and this is 1.5 divided by 4 multiplied by 2.5 centimeters. You can find x prime. Okay, so any questions on this? So, well, what is the next question? Next question: how much work must an external agent do to stretch the same spring 4 centimeters from its unstretched position? Okay. So, if you want to pull this free end of the spring by a force, let's say F, a distance of 4 centimeters, how much work, how much joules this force F do as a work? How much work does this force do if you want to just pull this free end of the spring 4 centimeters down? How much work do you have to do? Well, this work is already calculated in my pre-recorded videos. The work done on the spring is nothing but 1/2 kx squared. Okay, and since this x is just the measured from the equilibrium position of the free end of the spring, and this 4 centimeter will come to here. It is going to be 4 centimeters squared, but you have to convert this to meters. 1/2. Well, what is k? K is already calculated over here. Whatever this value over here, you put over here, and x is going to be 4 10 to minus 2 squared, and this is going to be work done by this force, which moves the one end of the spring 4 centimeters in terms of joules. Okay, and you can calculate this by putting this value over here. Anything? Any questions on this problem? No. Okay, let's erase. All right. So, do we have a next problem? Let's see. Yes, we have another problem that comes from you, one of your friends. It is, I think it's again chapter 7. So we're solving problems starting at 11 o'clock, and let's solve this problem for today. It's going to be end, and we will continue solving problems on next week. So the question is, Spider-Man, whose mass is 80 kilograms, is dangling on the free end of a 12-meter long rope, the other end of which it is fixed to a tree limb above, and by repeatedly bending at the waist, he is able to get the rope in motion, eventually getting it to swing enough that he can reach a ledge level when the rope makes a 60 degrees angle with the vertical. How much work was done by the gravitational force on Spider-Man in this maneuver? Well, it might be again difficult to understand the problem because it's long for you and because of maybe the English, but let me just put the question on this picture. So the Spider-Man originally right over here, okay, at this position, the rope is vertical, but while at this position the Spider-Man is just try to bend over to move himself in this pendulum motion and going back and forth, doing this swinging motion until he reaches to a level over here, so that this rope is making an angle of 60 degrees with the vertical. While doing this, well, this is what we do, right? As remember, when you're kids, you go to children play park and just go over to sit on a swing, and if you are alone, what you do is just try to bend yourself so that the swing is doing this pendulum motion, and you do your swinging and enjoy yourself. So what the Spider-Man is doing the same thing over here, the swinging motion. But the thing is, while doing this motion, of course, and since there are forces acting on the Spider-Man and there is this displacement, there's going to be work done on it, right? And the problem is asking not the work done by Spider-Man, but the work done by gravitational force. So there are forces involving in this motion, of course. One is that the Spider-Man is doing some kind of force applying on its body, because he's bending his body in some funny shapes, bending his waist, etc. So obviously he's doing some work because he's spending some force over it. This force is bringing him up in upward direction. But at the same time, we know that there is always this gravitational force which is constantly downward on his body, and obviously the gravitational force will do some work. And the problem is asking this gravitational force. Well, you have to be careful in this problem, of course, because we know the displacement, the actual trajectory. Well, you can take this problem as on just one motion, on one go, that the Spider-Man goes from this point until this point, but in fact, in reality, in order to reach this point, the Spider-Man is traveling on this path, many times, right? First, he's swinging little and increasing the swing motion more and more each time until it reaches to this point. So you can think that it is, going on this path many times, but since the gravitational force is a conservative force, and when calculating the work done by a conservative force, we don't need to worry about how many times it goes back and forth on the path. We only need to know what are the endpoints, what is the starting point, and what is the end point. Okay, we should only care about the endpoints. We don't should worry about how many times that the Spider-Man goes back and forth on this path, because the work done by the gravitational force is conservative, or the force of gravitation is conservative. Okay, so one thing is that is since we care about the endpoints, and we know that the gravitational force is always downward, and the work done by the gravitational force is nothing but going to be going in the vertical direction, because the gravitational force is in the vertical direction, and there is no any work done by the gravitational force in the horizontal direction. If you think only the endpoints, because the endpoints is such a way that the Spider-Man goes from this height, from this point, over this height to this point, and the displacement between these 2 points is just delta y, and the force acting on the Spider-Man by gravity is mg, which is downward. It's very easy to calculate it, because all you have to do is multiply this constant force, which is downward, by this displacement vector, which is upward. Well, the only thing that you should worry about the sign of the work. Obviously, the sign of the work will be determined by the direction of this displacement vector, and delta y vector, but its direction is going to be from down to up, while it's going in this direction, but I'm only thinking about the vertical displacement. In fact, the Spider-Man is traveling on this path, but traveling on this path, he is just changing its height from this point to this point, so there is no any work done by the gravity in the sideways, because the gravity is always downward. So in the sideways, in the sideway displacement, if you multiply the sideway displacement vector by mg, it's going to be always 0, because they're perpendicular to each other. So multiply this vector by this vector, which is both are constants, and since they are opposite to each other, this vector is in this direction, this vector is downward direction. So mg vector dot product with delta y is nothing but the magnitude of mg multiplied the magnitude of delta y multiplied by cosine of the angle between these two vectors, but these two vectors has 180 degrees, because one is this direction, the other is this direction. The angle is 180 degrees, and the cosine 180 degrees is nothing but -1. So that's why the gravitational work is going to be negative. So the rest is easy. Just put mg, the mass of the weight of the Spider-Man, 80 kilograms multiplied by 9.8 multiplied by delta y. The distance, this distance is what? So originally the rope length was just L, and this length is just L times cosine 60. So this delta y is going to be just L minus L times cosine 60, right? From geometry, I mean, you can easily figure this out from geometry. This distance is going to be L minus this part of the distance, and this part is nothing but L times cosine 60 degrees. So 80 times 9.8 times L is 12 meters, and 1 minus cosine 60. If you calculate this, you're going to find, well, you have also cosine 180 over here minus 1. You will find the work done by the gravity. Okay? I hope this is understood. The result is going to be minus anyway. I'm not going to do the calculation. You can do it yourself, because the rest is just playing with numbers. Okay, guys, so let's cut this lecture at this point for this week, and I will continue again solving problems that comes from you.
Hocam beni duyabiliyor musunuz?
Evet,
Benim bir sorum vardı da raporla ilgili.
tamam, onu cevaplayalım. Bir saniye şunu sileyim. Evet, buyur Berke.
Hocam siz şimdi birinci video için start ve end frame'leri aldınız ya.
Evet.
13 ve 76 olarak.
Evet.
Ben diğer videolarda start frame'leri 13 mi alacağız hepsi için?
Hayır. O sadece birinci video için öyle. Diğer videolar için o değişecek. Burada sadece dikkat etmeniz gereken şey, bu start ve end frame'leri nasıl belirleyeceksiniz diğer videolarda. Diğer videolarda şöyle belirleyeceksiniz. Hani araba var burada, işte ilk başta araba var. Bir de parmak var üstünde. Parmağı bırakıyor ve araba gidiyor ya. Parmak şu hareketi yaptığı, tam şu hareketi bıraktığı frame'den bir önceki frame'i starting frame olarak alabilirsiniz. Tamam mı? Gidiyor. Diğer kütle yere çarpıyor. Şeyi tutan, yeşil arabayı tutan ip gevşek hale geliyor. O gevşek hale gelmeden önceki, yani her zaman bu ipin gergin olması lazım. Gevşek hale gelmeden, yani hanging mass, aşağı doğru giden kütle yere vurmadan önceki frame. Son frame'iniz olacak. Son frame bu. Bu kütle yere vurmadan önceki frame. Tam olması şart değil. Yani birkaç frame öncesi de olabilir. Yani tam almak zorunda değilsiniz. Ama şu birinci frame olarak şu araba harekete başlasın. Yani harekete başladığı andan itibaren birinci frame'i alın. Yine o da tam olması şart değil. Önemli olan arabanın hareketi az da olsa başladığı ve sallanan kütlenin de yerden önceki, yere vurmadan önceki birkaç frame öncesi. Başlangıç ve bitiş frame olarak alabilirsiniz.
Çok sağ olun, teşekkürler.
Tamam.
Hocam ben de bir soru sorabilir miyim raporla ilgili?
Tabii.
Hocam Pretlab soruları var ya, onun sanırım 3. sorusunda bir soru var, diyor ki arabadan sallanan cisme kütle transferi yapıldığında diyor. Bunu
Evet.
tam olarak nasıl alacağız? Yani o kütleyi tamamen ona mı ekleyeceğiz, yoksa hani bir kısmını mı? Ya onda çok kafamız karıştı da yapamadık onu.
Tamam, bir dakika göstereyim sana. Şeydi. Evet. Second'da. Şimdi buraya gelecek olursak, kaçıncı soru demiştin? 3. soru mu?
4. soru hocam.
4. soru. Tamam. If the mass is transferred from the car to the hanging mass, how will each of the following change? Will decrease, increase or stay the same? Mesela burada fazla büyütmüşüz. Evet. Burada bazı kütleler var. Üst üste diskler var. Başlangıçta diyelim ki burada 3 tane disk var. Tamam mı? Arabayla başladınız. Bıraktınız. Bu aşağı doğru gitti. Araba sağa doğru gitti. Bu 3 disk buradan. 3 diskten bir tanesini bir dahaki sefer yine açacaksınız. Tekrar geri başa sarıyorsunuz. Bu sefer bu disklerden bir tanesini alıp arabanın üzerine koyuyorsunuz. Sonra tekrar serbest bırakıyorsunuz. Sürekli her defasında aşağı doğru sallanan kütleden bir disk alıp şeyin üzerine koyuyorsunuz. Yeşil arabanın. Her defasında bunu yaptığınız zaman diyor ki 4. soruda mıydı? Nerede? Evet. Total mass of the system değişecek mi? Her defasında bunu yaptığınız zaman. Acceleration of the hanging mass değişecek mi? Bir de toplam sistem üzerinde hem araba ve hem de hesaba katarak hanging mass hesaba katarak bu sistem üzerindeki net kuvvet değişecek mi? Bunlardan hangisi değişecekse değişecek. Nasıl değişecek? Azalacak mı? Artacak mı? Soru bu.
Hocam ama burada diyor ki transferred from the car to the hanging mass diyor. Yani arabadan sallanana dememek istemiyor mu? Yoksa ben
Tamam, tam tersi diyor. Evet. Burada arabada bazı kütleler olduğunu düşüneceksin o zaman. Tamam mı? İlk başta bazı kütleler var arabanın üzerinde. Bırakıyorsun, sonra ikinci defa bırakacağın zaman arabadaki o kütlelerden bir tanesini alıyorsun, buraya getiriyorsun. Diskleri diyelim ki. Sonra yine bırakıyorsun. Sonra ikinci defa da yine buradan alıp buraya getiriyorsun. Anladın mı? Şöyle düşüneceksin. Arabanın üzerinde bazı kütleler var, diskler. Diyelim ki 3 tane disk var. Bıraktın. İkinci defa yaptığında bu disklerden bir tanesini alıp şeye getiriyorsun. Hanging mass'e takıyorsun. Bırakıyorsun. Sonra bir dahaki seferde yine aynı şeyi yapıyorsun. Bunu yapıyorsun. Yani fark etmez. İster buradan al buraya ekle, ister buradan al buraya ekle. Ama tabii fark edecek. Buradan alıp buraya eklediğin zaman bu sefer net kuvvet artacak mı azalacak mı orada değişiyor. Yani birisinde artıyor, birisinde azalıyor. Eğer buradan buraya getirirsen birisinde artarken diğerinde buradan buraya getirdiğinde azalmış olacak. Hangisi ona artık sen karar ver. Yani demek istediği şey toplam kütleyi değiştirmiyorsun. Hani bir tanesini cevapladım zaten şimdi.
tamam hocam, onu zaten
Sistem
tamam.
ivme her defasında arabadan buraya aktardığın zaman kütleyi ivme nasıl değişecek? Her defasında arabadan buraya kütleyi aktardığın zaman net kuvvet nasıl değişecek sistem üzerindeki? Bunu cevaplayacaksın.
Tamam hocam. çok
Tamam.
teşekkür ederim.
Aha. Sesin çok kısık geliyor yalnız. Sesini biraz yaklaştır.
Ben de bu 4. soruya
Biraz daha yaklaştır. Duyamıyorum sesini.
şimdi nasıl geliyor?
Biraz bağırarak konuş.
Hocam
Evet, şimdi iyi. Evet.
diyor, kütle arabadan asılı kütleye aktarılırsa diyor.
Evet.
Yani biz burada boşluğu mu çekmiş oluyoruz? Diğer hani belli bir kütlesi var olarak söylüyor ve biz bu kütleyi tamamen arabadan asılı kütleye aktarılırsa diyor.
Evet.
Yani burada A eşittir direkt serbest atış şeklinde mi ilerlemiş oluyor? Öyle olursa eğer T gerilmesini sayamayız. Boşluğu çekmiş oluyoruz.
Serbest atış yok. Yani sen hiç herhangi bir videoyu izledin mi bunun videolarından?
Evet, evet izledim.
Şimdi serbest atış falan yok. Her zaman arabayla asılı kütle her zaman iple birbirine bağlı. Sadece yapman gereken arabanın üzerindeki, diyelim ki arabanın üzerinde kütleler var. Her defasında bu kütlelerden bir tanesini alıp şeye koyuyorsun. Artırıyorsun, bunun kütlesini artırıyorsun. Bunun kütlesinden aldığın kadarı sallanan kütleye ekliyorsun. Her defasında bunu yaptığın zaman ne değişir? Serbest atış yok.
Tamam ben tamamıyla M2 kütlesine M1 kütlesine aktardığımı düşündüm. Hani
Tamamıyla değil. Tamamıyla arttırılmıyor. Yavaş yavaş. Parça parça. Burada parçalı kütleler olduğunu düşün. Bir parçasını alıyorsun buraya koyuyorsun. Bir parçasını alıyorsun her defasında. Bunu yaptığın zaman ne değişir? Nasıl değişir? Onu soruyor. Yani tamamen bütün kütle, arabanın bütün kütlesi tamamen buraya aktarılmıyor. Anladım senin sorduğunu. O değil. Yavaş yavaş. Tamam. Evet. Is there any other questions regarding reports or any other questions you want to ask? If not, I will stop here for today, for this week, and next week again we will continue our lecture by solving some problems that come from you. Okay, also from I select some question maybe. Okay. All right, guys. That's okay for today. For those of you who joined the live class, thank you.